Hi everyone, welcome to this talk. I'm Xiang from National University of Singapore. I'm going to present our work feedback-driven semi-supervised synthesis for program transformations. This work was mainly done when Shraddha and I were interns at Microsoft. We have seen an emerging trend of tools and techniques that synthesize program transformation using examples of code edits. For instance, GetFix has been developed at Facebook. It uses examples from code repository to learn bug fixes, and Blue Pencil from Microsoft uses examples to learn program transformation to automate repetitive code changes. It has been released in Microsoft Visual Studio as IntelliCode suggestions. Usually, those techniques tend to overfit to the example. That is, the synthesizer program works on the given example but cannot be generalized to other inputs. Let's first see an example of this problem in IntelliCode suggestions and our solution to it.
Hi everyone, I'm Gustavo Soares and I'm gonna show you a demo of IntelliCode suggestions. So I'm in the middle of a refactoring here. I deleted this class and now this method is an instance method of model. So I'm gonna move model from here to fix this method invocation. And I have to do the same thing to the other invocations that were following this old pattern. So let's go to the next location. Here is the next location. I have to do the same change. So, okay, I'm done here as well. This is kind of a repetitive task, right? It's boring and time consuming. But luckily, IntelliCode was watching what I was doing and it produced suggestions for me to automate the rest of the change. So I can navigate to the next location, and instead of applying the change manually, I can just look at the suggestion that IntelliCode produced, review it, and apply it. I can even apply all of them at once. Cool. So IntelliCode was in the background watching what I was doing, and it used my changes as examples to synthesize a program transformation, and then use this program transformation to produce code changes in this file and show to me as suggestions. Cool, but my job actually is not done yet. IntelliCode missed some locations. If I go up here in this file, we will see, yeah, this is another location that follows the same pattern, but IntelliCode did not produce a suggestion. It's a false negative. It's a different method, but I have to do exactly the same thing. Now I have to give another example to IntelliCode, and hopefully IntelliCode with 3 examples will synthesize a new program transformation and will automate the rest of the changes. But the more examples I have to give, the less useful is this feature for me, because there are fewer locations to be automated. But what if there was an easier way for me to demonstrate my intent without having to provide the full input-output example? For instance, the cursor location can indicate an input where the transformation should be applied. And this is the key idea of this paper. We are proposing a semi-supervised synthesis technique that combines input-output examples with additional inputs extracted from different sources, for instance, the cursor location, to synthesize a program transformation. So now IntelliCode is using this technique, and if I just start making the change to this location, IntelliCode will immediately produce a suggestion for me. It uses the cursor location to extract the input, potential input, and the additional examples that I gave previously to synthesize this program transformation. In this way, I don't need to type this change entirely. I can just accept the suggestion and finish my repetitive task using fewer examples. I can apply all of them here. Cool. Now Sheng will explain in more details how this technique works. Thank you.
Yes, now let's see what happened on this demo. As shown in the demo, we first manually perform 2 edits, and then Blue Pencil synthesizes a program for the transformation. In our case, we have a domain-specific language to specify the transformation program. But for simplicity, we describe the program as a template, which shows the structure of code before and after the edits. In the template, x1, x2, x3 are three identifiers, where x1 represents the method name get model training permissions, x2 is the first argument model, while x3 represents the second argument. Since the value of x3 in those two edits are different, x3 doesn't have a uniform value. However, the synthesizer transformation using two edits may fail to transform some inputs, such as this one. It should be transformed via the same pattern, but Blue Pencil produced a false negative here. The main reason is that the predicate on x1 in the program is too specific. It requires the value of x1, that is the method name, must be get model training permissions. However, the additional input has a different x1 value. Now let's see how our approach can be helpful for such kind of cases. Inspired by semi-supervised learning, which learn a model from both labeled data and unlabeled data, we propose a semi-supervised synthesis. Our semi-supervised synthesis generates a program using both input-output examples and additional inputs. The input-output example corresponds to labeled data, while additional input corresponds to unlabeled data. Our main insight is that the additional input can help us disambiguate how to generalize the transformation by providing more inputs that should be manipulated by the transformation program. Now we have another important question. How can we generate additional inputs? Here we propose to find additional inputs in a feedback loop. With the input-output example, synthesis engine first synthesizes a program, which is then used to the input pool. If the program produces a false negative, that is the input that should be transformed, but the program failed to transform. Then we add it as an additional input. This process continues and the program keeps refined with the goal of synthesizing a better program. Now let's first focus on the semi-supervised synthesis. Given a set of input-output examples and one additional input, our main idea is to use output generalization technique to generate the output for the additional input, and then we can synthesize a program based on both given input-output examples and additional examples using existing synthesis engine. In our running example, given some examples and additional inputs, our goal is first inferring the additional output. We then invoke existing synthesis engine like RefZ with the original example and the additional examples. To infer additional output, our first step is to perform provenance analysis. Provenance analysis aims to determine which fragment of the output depends on which fragment of the input. Specifically, we calculate a map between the input-output. Recall that we have synthesized a transformation. Actually, we could easily extract the input-output fragment mapping from the transformation program. In the running example, we have three maps, which corresponds to x1, x2, and x3. Then we use anti-unification model provenance to find generalization of input and additional input. Basically, the anti-unification algorithm compares the elements of two inputs and substitute the different elements with the whole. Our algorithm works on AST, but for simplicity, we are showing as code. In the running example, firstly, we can see the method names are different. Therefore, they are replaced with a whole represented as x1. We then created two substitutions representing the substitution operation for input and additional input respectively. Similarly, the second argument are also different, so they are replaced with a different generalization x3 and update the substitution. Different from traditional anti-unification, we just substitute the provenance node. This is to avoid overgeneralization, such as generalizing the whole inputs. As we shown before, the synthesis program is too specific and cannot be applied to the additional input directly. Now we can use identification to help generate additional output. Identification generated two hosts x1, x, and x3, which means the predicate on x1 and x3 in the program is too specific. Therefore, when we apply the program to the additional inputs, instead of using the predicate of the program to evaluate x1, we use the substitution function, which maps the value of x1 to its training on the way. Similarly, we also need to evaluate x3 using the substitution. After the adjustments of the program execution, we can then produce additional output. With the additional example, the synthesis engine Raffazi will produce a better program by generalizing x1. The refined program can be then properly generalized. Now, let's see how we can use a feedback loop to automatically find the additional input. The first feedback could come from users. That is, we can involve human in the loop. In this setting, for a given input pool, we allow user explicitly specify the input she or he wants to transform, and hence we can then take the user-provided input as additional input. Since users may have difficulty to find additional inputs, we propose a semi-automated feedback to automatically determine additional input at the cursor location. The user's cursor location indicates that the user will likely modify this location, but they may not know existing transformation can be applied here. Our tool runs in background, goes through all candidates' additional input at the cursor location, and automatically determine the correct additional input using a reward function. The reward function combines clone detection with our provenance analysis to measure the similarity between candidate additional input with past examples. If one candidate's additional input is similar with any previous example input, it is likely to be an additional input. I will skip the formal definition of reward function, which can be found in our paper. In this example, suppose the user's cursor location is at the last line. Then the candidate's additional input could be the whole invocation statement, the member access expression, or the variable. In this case, reward function determines the whole invocation statement as the correct additional input. The synthesis engine is then triggered with the invocation statement as additional input. At the same time, it will produce edit suggestion at the cursor location. Actually, we have a fully automated feedback which doesn't even require cursor locations. Due to time limit, I will skip the fully automated feedback. To evaluate our approach, we designed several experiments, but here we just focus on two of them due to the time limit. The first experiment evaluates the effectiveness of semi-supervised synthesis, and the second experiment evaluates the effectiveness of semi-automated feedback. All the experiments are conducted on real-life code editing sessions from Microsoft developers. In the first experiment, in each scenario, we give a set of past edits and some inputs that should be transformed. And then we compare the transformation, recall, and precision with and without additional inputs. With the help of additional inputs, we found that our approach significantly improved the recall of baseline approach from 27% to around 100%, while retaining the high precision in generating correct suggestions. In the second experiment, in each scenario, we give a few past edits and one cursor location. We then evaluate whether we can produce correct transformation at the cursor location. Out of 295 scenarios, our tool only produced one false positive and three negatives. On conclusion, existing program synthesis may produce overfitted program. To elevate this problem, we propose semi-supervised synthesis. We then propose a feedback loop to generate additional input. We implemented our idea as a Visual Studio plugin. The evaluation results show that we can improve the recall without a significant loss of precision. If you are interested in this paper, you can find more information about Blue Pencil project and the Microsoft Pros team here. Microsoft Pros team is also hiring interns. If you are interested, please connect with any author of this paper from Microsoft. This is all my presentation. Thank you for your attention, and I'm glad to take questions.